you really?
I'm selling that
I'll take money.
selling that leafly shit right there.
Okay, well that means you're probably stuck helping in your life, but also in here, so you'll see a lot of it this summer.
Oh yeah, no, $15 an hour.
I'll be here for the whole day.
Alright,
No, I didn't.
let's get started. Gravitation isn't bad, we can go through it. Circuitry, most of you have done some work. Electromagnetism, I put waves here even though it's not wave structure. All these things actually work because of waves, you just don't know that. So what we're going to talk about with E&M are things like electric field, right-hand rule, conventions and circuits, things like that. It's not actually lambda, nu, and all those things. There's stuff from like the very beginning here. Okay.
This just sounds hard.
Wilson's people, you also have like 1 day of quantum mixed in. Yeah, but okay, so you just have what? Schrodinger, Heisenberg, and dilation, right? Yeah. We can talk through that. Okay. Alright, these are the 3 topics. Where do we want to start? Where's the thing that scares us most?
Gravitation. I don't even remember gravitation.
What? Yeah, all of them, good. Okay, gravitation seems to be the kind of cohesive word. Okay, gravitation, there are 3 things about that you really need to know. Gravitation has a formula. Big G, M1, M2 over R squared equals the gravitational force. That's Newtonian's gravitation. Newtonian's gravitation applies to 2 bodies. I can't have a gravitational force from 1 body. It has to have 2. It doesn't matter what they are. I don't care if they're planets or satellites or your mom. I don't care. As long as they are things with mass, they are going to attract each other. I don't care if it's an atom and the sun, they have a gravitational force between them.
Oh, yeah.
And so M1 might be way, way bigger than M2. That's 2.
Hey, you're late.
And the distance between them, we're going to call that R. And the key thing about the distance between the bodies is it's not the difference between their surfaces, but instead between their cores. You have to go to the very center of a sphere. So if you're coming in here, you're actually measuring R1, R2, this is tangent, and your thing is up here. So your R is actually this whole thing. And that's going to be the only spot that most of you get tricked on.
How many questions are like this on the final?
Oh, I don't know. I think I told you there are 5 gravitation questions. 6.
That's 5.
So if I give you a workout problem like this, I probably would give you the distance between 2 bodies, and maybe from their cores, and maybe from their surfaces. And we're going to work through it. The key thing here is this G is a tiny number, 6.7. Oh no, 6.2. I think.
Are we gonna have that memorized?
No, it's given to you. It's in the negative 11. The key thing is it's a tiny number. I don't care exactly as long as I don't care about its units. If you really care about its units, it's physics.
Alright, what are the rest of those? R is great.
Radius.
R is radius, M1 and M2
Are the mass of the 2 bodies. So do we want to work a quick problem?
Yeah. Are we going to be given M's?
Sure, yeah. So
Or we have to find
let's
them?
just work a basic problem on this guy really fast. It's best for you to do like an exercise where you do the example and we check it against it, yes?
Yeah.
Okay, so let's just come up with a simple problem that's kind of representative. This is the Earth. It has a radius of Earth is going to be something like, I don't know off the top of my head, this is 24,000.
Yeah.
No, that's the circumference of Earth.
Oh.
4,000. 4,000, okay. Radius of Earth equals 4,000 kilometers. And let's say I've got a satellite orbiting out here at another, let's say 6,000 kilometers. It's way out there for some reason. So 6,400 kilometers between the 2. And this is, let's say, 10 to the 31st kilograms. And this is, I don't know, 500 kilograms. Let's not be too hard. Find force between Earth and Saturn.
You wrote 400 and said 4,000.
Nick,
No,
you silly
400
dude.
kilometers would be the right thing.
Hey, Ori.
Yeah, it's 4,000. Thank you.
4,000 cents.
Okay, so if you can't understand my shorthand, here it is audibly. You have a 500 kilogram satellite orbiting 6,000 kilometers above the Earth's surface. Given that the Earth's radius is 4,000 kilometers and the mass of the Earth is 10 to the 31st kilograms, find the force between them.
Are you sure that the gravitational constant is 6.2?
Could be 6.7.
What about 6.9?
You can use whatever you really damn care about. As a physicist, I really only care about this part here, let's be honest.
Wait, so it doesn't really matter what the number is?
Well, I mean, you're talking about something that's negative 12 power.
Smile.
And you're off by a factor of 100 here, and you're only off by a factor. So it's only a change of factor like 5%.
So we actually could do 6.9.
Sure, 6.9 is not going to change your answer appreciably. You could use 10 for like as long as I'm in the right neighborhood, right? Okay, so if you get the actual value, the key thing is that you know it's a small number out there. Okay, so give this a try. It shouldn't be too hard. Again, I've got 4,000 kilometer radius of planet. I have 6,000 kilometer radius of orbit, and I've got a very different mass system. Just use your phone or your iPad right in front of you.
Nendick, I hope no one's using this because I'm stealing it.
It's fine. Okay, the key thing here why you're doing this, and this will be important, especially the Wilson students, but to mine as well, is that the force between both of these is equal. If you want to find the force of the satellite on the Earth or the satellite on the Earth or the satellite, it doesn't matter. They're exerting the same force. It's a mutual force. What's not equal is the acceleration. They have very different masses, F equals ma, but they do have the same force. Of course, the satellite's accelerated orders of magnitude more than the Earth. Otherwise, some weird. Yeah. So the idea is that I am orbiting 6,000 kilometers above the surface and a 4,000 kilometer planetary radius. Yeah, 10,000 together.
Wait, 10,000 squared?
10,000 kilometers, mind you. Yeah, 10,000 times 10 to the third squared. All right, give this like 5 minutes or even less. We'll respect your time and mine.
I'm gonna be here all night partying it up.
Oh my God.
3.35.
I don't know off the top of my head. No, we'll knock it out here really fast.
Wait, so it's in meters?
Yeah, R must be in meters. So I will take, and we'll do this one carefully here on the drawing here instead of just like scrawling notes. Yeah, R must be in meters. We're in physics.
Nendick, how do you do E times
You
on
can
your
just multiply your answer by what, 9? What's up? What's your question?
How do you use the?
It's left of 7.
I know, but how do you use that? Do you use that before?
What's kilo for? Kilos is third, yeah. Alright, would it be good for me to start working this through?
It gives you like 5,000.
Alright, F equals big G, M1, M2, R squared. This is called Newtonian's universal gravitation, and the equation here should be pretty straightforward. So, F equals, we said 6.7 times 10 to the negative 11th. That's something you'll be given. If you're in my class, I assume Wilson as well, as long as he's not giving you, like, ones you write out. As long as he's giving you my equation sheet, you'll get it. What's up?
Wait, so are all the equations underneath problems you're going to give those to us?
Yes, you have a copy of it on your email too.
Are we getting to use the equation?
Yes, you have it. You'll be printed out for you, Eris, but you have a copy of it.
You like telling schools to us because you didn't do that. You're going to give it to us tomorrow.
So that's what I have it for you. It's printed. It's on like bright pink paper or something.
I don't know. So, that's good. I've already tried.
I have no idea who's. All right, gentlemen. Very quickly, masses in physics are always in the same unit, which is kilograms. So I don't have to do any work here. I have 10 to the 31st times 500. Even that 500 here is pretty irrelevant. I can replace by 1 and get pretty much the same answer. I mean, right, this is 29 orders of magnitude bigger. So if I multiply it, I'm not changing the order of magnitude significantly. 1 or 2. My radius needs to be both of my radii combined. I want you to do that r squared for a moment so we're clear what's going on. All right, gentlemen, this is your time, but let's use it together. Negative 11. So if I take like 10 to the power of 31 and multiply it by 500, I get 5 to the 33. So I get F equals, and I can go ahead and take that times G while I'm at here. 6.7 times 10 to the power of negative 11. I get 3.35 to the 23rd. 3.35 times 10 to the 23rd. Over that r squared. Now my r is 4,000 plus 6,000. We all agree with that. Times 1,000. Because it's in kilometers, I need to make it meters. So you can put this, right, you can make this into 4 million and 6 million, or you can just write it this way. However you do that, you're going to end up squaring those meters. Okay, that's a huge number. Yeah, but I'm starting off with 10 to the 23rd on top, so it better be a huge number.
Could you just turn it into meters before?
Yeah, you could. You could easily make this 4 million plus 6 million, make 10 million.
Wait, Nendick, why did you multiply by 1,000 on the bottom?
To make kilometers into meters.
Wait, why do we need to do that?
Because we're in physics, and our
that's how it
unit of
works.
length is always meters. That sucks.
So what should it be?
Yeah, it fucking sucks,
So I divide that out by 10. 10,000 times 1,000 to the power of 2.
100,000.
And I get an absolutely freaking huge
10
number,
million.
which is not right. What went wrong? Oh, like
You use some pretty freaking insane numbers,
Probably
Tim.
you could use 6.9.
it didn't do that. Well, what the hell? Did I get the mass of the Earth wrong?
What'd you get, homie?
Oh yeah, no, we're off by 10 orders of magnitude on the Earth's mass. So we're like orbiting a black hole.
Oh, of
Mr. Nendick,
course.
what
So-
physics were you smoking last night?
Good physics, apparently. Okay, so the correct answer should come out to,
Chemistry.
even though, okay, this is obviously now, because this is off by basically 10 orders of magnitude,
Wait,
we
wait.
have just a fucking huge number, which is not what you're going to get in real life.
Well,
it would be
what?
3, 3, 5, 1, 2, 3, 4, 5, 6, 7. Which
Nendick,
should
what's
terrify the living hell out of you. If you're actually in this orbit, that acceleration would likely tear you into your elementary particles and turn you into light.
No balls in one.
I don't even know this. I don't even know this. This is shit
I need to know.
Yeah, I don't want to do this.
6 times 9. Okay,
What's
this is all that's going on.
What's the unit for force again?
Force, newtons.
And let's make sure that that's the only mistake that went on there, because that's...
It's a pretty big mistake, Tim.
Well, to be fair, being off by 7 orders of magnitude is a pretty big mistake.
So is that?
Yeah, this is Newtonian
Wait,
gravitation.
can we just subtract 7 from that exponent then? From top?
Mr. Dick, why are you burning a giant gummy bear?
Science.
You might-
We'll do it tomorrow, because if we did today, we'd blow a hole in the parking lot. Right?
What?
It's chloride. Okay, so, we're clear here. Do we need to try another one with more reasonable numbers?
Yeah.
Yeah, what's the-
It was like that.
It wouldn't hurt.
I mean, I say we do
What's
another
that?
one with reasonable
What's
numbers.
the unit on that?
Newtons is in force.
Mr. Nendick,
What's up?
how basic are the numbers? Like, are there gonna be like a lot of
They'll be on the scale of planets.
Are they gonna be like a lot
That
of
means
kilos
nothing.
or?
Yeah, we're not going to do anything really crazy to you. They'll probably be kilos, or we'll write them in scientific notation already. The key thing is we'll probably make them based on like planets and moons or planets and satellites, real life things. I'm not really going to be interested in what's the gravitational force between these two extra markers. Yes, there is one, but no, it's...
Is that the only possible gravitational problem?
What? Yeah, that's really about it. I'm not going to make you solve for n in this equation.
What about the two, like,
Same.
Are you gonna do like multiple planets?
We have a couple extra problems.
There'll always be a two-body system. The three-body system is way.
What's on my phone?
We did with charges.
So I'm guessing on this one.
What's up? That's it.
Oh, the equation wheels like pretty good.
Yeah. All right, gentlemen. Quickly. Okay. There also is a second topic of gravitation, which is our dude Kepler. If you don't remember Kepler, he turned out to be pretty important. Kepler really has 3 key postulates. 1, everything that orbits does so as an ellipse. So I don't care if it's a circle. A circle is just an ellipse with its foci overlap. So if something's orbiting, it's moving in a damn or a damn ellipse in an oval. I don't care if it's a comet. I don't care if it's a satellite. I don't care if it's a planet. If they've got 2 orbiting bodies in space, they're orbiting each other in an ellipse. And 2 was the equal area, equal time thing, which is actually drawn up on the other board already, which just says if I cover this amount of time, let's say in a month, I have to cover an equal area here in a month. You know, in theory, these 2 areas should be equal. The point is my velocity changes. What doesn't change is this area that I sweep out, this integral, which gives us the 3 halves law, which both Will and I don't care about. That's in our science law. Okay, the key thing with Kepler is when you're thinking about orbits, when you're thinking about, okay, how do I do these things? You just need to think through and say, of course it's going faster when it's closer and slower when it's farther away. It's the only thing that makes logical sense, right? Just like if I'm swinging something around my head with angular rotation. Yeah, they're slower when it's farther away. Quite the opposite, right? If I have a toy plane on a string and I'm swinging around my head and I make the string shorter, it has to go faster too. That's really all there is to gravitation.
Will there be a workout problem with that?
At least for my test, yes.
Yes. So then how the hell would you do a workout problem with that?
What type of questions would you have with those?
These would be multiple choice. Like, are these areas greater than, less than, or equal to? True or false, the time period in these areas is the same if they're the equal area, something like that. I don't know exactly.
Nendick.
There's no true and false.
So for is there gonna be a question like
No workout. It would all be all ideas.
Okay, and so that means there'd be multiple choice?
Yeah. Yeah, workout multiple choice. Again, the key things, like takeaway, Mr. Nendick, I've not been paying very good attention, people are talking, whatever. Here are your key takeaways. One, make sure you can manipulate this equation with real numbers instead of fake ones.
You have to do a derivative.
No, you have to touch derivatives. Two, you're in a general class. Two, take away that things are elliptical and that equal areas for equal time. Take away that in Newtonian gravitation, the force is the same in both directions. It doesn't matter if you're on the planet or the moon, the forces are equal because that's how physics works. Because these two things are multiplied with each other, I don't really care which order you multiply them in. What's up?
Can we do like an electric field workout?
Yep, we'll do some. We'll play with this.
Hey, can you wait? No, jeez.
Hey, none of us are smart.
All right, gravitation, good, bad, and different.
Moye? Good.
Good. Okay. From there in this class, we moved on to rotation. Things like omega, L, moment of inertia, gyroscopes. Again, we said we're not going to put those on the test. So if you're concerned or studying those are not the spot you need to study. We said this would be a field and gravitation test.
It's like Or tries to cuss and
And so we don't need that.
Or it's like Nendick.
In college,
Nendick.
you would take that rotation first semester. And it would go in with the dynamics and kinematics. Okay, the next thing we did is we started to define electric charge and field. And this is where things started to get a bit weird. So what I would suggest before we do workout problems, I will tell you at least on my test there's a matching section. I'm pretty sure on Wilson's there is too. I have not seen his test recently. Okay, it's over units. You need to know your units. Let's just try together as a class come up with as many units as we possibly can. Make sure you have a list. Make sure you have these memorized. I'm not giving you them. So unit of, let's say, force. Force, good. How about charge? Good. How about capacitance? Farads. How about resistance?
Ohms.
Good. Resistance is the ohm. How about magnetic field?
Tesla.
Good. How about magnetic flux? Oh shit.
What's his name? What's his fucking shit?
I don't know what it's called.
Magnetic flux is equal to the Weber,
Yeah.
or in my class, the Tesla meter squared, because the Weber is a stupid ass unit.
Yeah.
Okay, make sure you got it down. How about things like the electric field?
What's cap stand for?
Oh shit, I don't remember this. That's going to be newtons per coulomb. Newtons per coulomb. Okay, that's an important one. Things else that could come into play. Let me make sure that I have.
Things that else that could come into play. Tim's
Yeah.
English is spot on.
So did you say these ones are all going to be matching?
Yeah.
And it's like a 10.
So there's 10 so there's 5.
Give me about 30 seconds. So what I want to do is make sure that I'm not misleading you down a primrose path and telling you, okay, you need to know this thing.
Yeah, I know. Also something else. It's like
30 seconds. While we're going, we still have plenty more units here. How about current?
Amps.
Good. The amp. How about things like, mass is always in kilograms. Length is always in
Meters.
good. And there's still quite a few more than these, which I want to make sure that I'm not
How many are on the actual final?
10 for you guys.
watts is joules.
Watts is joules. Good. So how about work? Is joules. Power is watts. Be careful not to confuse those two. That's a common mistake. Good. Potential energy is also in joules.
We're gonna need to know like PE 0 plus KE.
Volts, good. Potential? You get the idea. There's a lot of them, but once you get going, it's not too bad.
Is that all we'll need, or?
Probably. I'm making sure I'm not missing any here.
What's potentially?
Yeah.
Email me
Just
that.
take a peek.
Yeah, I thought I already did. Power potential versus.
What's potential stand for?
Potential is the amount of charge difference between plus and minus. It's equal to the, oh, like you're asking what it stands for?
Yeah.
The volt. I always give you both the name and the symbol.
Hey, we're shut up.
You're gonna make sure I have it right. Sorry.
Okay, I think that covers everything we've covered this semester in terms of units that you're ready to care about. Obviously, there's a lot of angular units that we're omitting because we're not doing angular. Theta, omega, L, I, all that jazz. Okay,
All that shit, Tim.
that's a lot. Now,
Shit,
if
I'm
you are
just-
completely, like 30 seconds aside, if you feel like you're completely screwed on a physics test, you're just pooping yourself on a workout problem, write down the damn unit it's going to be. You just write, I have no clue what's happening, but I know the answer's in amps. I get half a point. Okay, that doesn't sound like a lot.
Tim over here working.
But it's there, right? Tell me you know something, and then you can work backwards. Well, if the answer's in amps, I know I'm looking for the variable I. Wait a minute, I've got this.
We get that wheel, right? Yeah, cool.
Yes, you get this.
We get them.
I get it.
Okay,
Nendick,
we good
get
on
the
units
wheel.
before we go into charge? What's up?
Yeah, we're good.
Okay, now, in charge.
The next section is on vaping.
Back to back.
Those are in your calculator?
In charge, we have two conventions.
Oh, I hate this shit, Tim.
We have a convention that a charge, the electric field will leave the plus and go to the minus, which is another way of saying I can make connections. And you start to remember drawing these fields and the nightmares those were. At least you had to calculate them by hand. It could have been worse. Okay, remember this. My class, Wilson's class doesn't care about my class. This is a dipole because you got the loops.
The dipple.
Okay, remember you have lots of different kinds of electric fields, and at least for Wilson's class, I know you're expected to know how to draw these offhand. My class, I more care about you identifying pluses. They're going to make an asymptote, right? Minuses, they're going to do the same damn thing. They're going to run into each other and try to come apart, and that's because charges work like springs. Okay, two like charges, if you try to squeeze them together, they're going to sit there and push harder and harder against you. You have to do work. You have to increase the potential energy of a system to bring like charges together. The same thing with unlike charges, they want to be together. So if you have to fight nature, if you have to do the opposite thing nature does, then you're doing the work. Then you're changing the potential energy. So like charges, as you move them apart, increase potential energy, increase the amount of work you have to do. And this should be logical to you. Just think about it as a spring. So with unlike charges, you're stretching the spring. With like charges, you're trying to compress the spring. Both things, you're storing potential energy in the system.
Nendick, so for those diagrams, they're the exact same for both of them?
Yep.
So there's more.
There's no way to know. There's no way to know that these are the same damn thing, minus the fact that these should technically.
That's what I thought. That's what I thought.
Yeah. And I don't care about that. Now, what I need you to know, from my class at least, is that the minuses point
That's right.
in and the pluses point out. I'm sure that there's similar things. When we were in this area, we talked about we talked a lot about how strong the electric field was at a given point. So we would draw in some kind of an electric field. Let's just choose the simplest electric field of a dipole.
It's a good drawing, Tim. Fuck, I always forget.
Alright, so that is the simplest electric field you can have. And recall the kinds of boring but useful problems where I
Oh, I
would give
hate
you like
that shit, Tim.
different areas on the board and ask you to rank it in terms of strength. And of course the strength is just the closer the damn lines are together, the closer or the larger the field is going to be. So in this one they're ranked in order ABC.
Oh, shit, that's not hard.
And this should be coming back to you in troves. Like you should be pretty happy with where you.
Would it be ABC or?
Yeah, ABC in this case.
Wilson?
Especially if I throw in another line here, right?
I would.
Why? Because there would be a pretty tight grouping here. Just not how I've quite drawn it.
So it's
What is this
closer.
called? I've never seen it.
Well, it should basically be ABC in this case. It should be clear that A is going to be the most as it's closest to the charge. depending how it's drawn, it will be exceedingly clear. Let's say I just didn't draw that line in there. What's up?
Okay, well, Wilson said that B would be like the least because it cancels out.
As long as let's move B a little bit so it doesn't go against that description. Does that make sense why they be ABC? It would cancel out there B in a opposition is probably what you're thinking. So if you have the one that looks like this, the saddle point there would be 0. That's my guess is what you've got crossed. In a dipole, there'd still be some force there just because, unless you put it directly in the middle of the dipole. But here there's no ambiguity how it's drawn.
So it's just the more fields are closer together.
Yeah, the more lines are close together, the more the electric field has strength. A dipole is loops. Anything that's got a plus and a minus, anything that's got loops.
And so the closer in the middle it is, the more.
In a dipole, all the lines theoretically connect. A dipole is actually a solenoid, now that you know those words.
You try to teach us that, but I don't think anyone knows.
Yep, we're getting there. Okay.
Nendick, slow your bitch ass down. What'd you say, Nick?
The vowels.
What was he trying to say about that?
So the next thing we did, remember both Wilson and I brought in the pipe and we rubbed it a lot and we levitated things around, right? So, yeah. Okay.
That's a big ass bomb.
So, remember we did that, and we're talking about how like charges repel and unlike charges attract. And what was happening wasn't that we're like inducing a current or anything. What we're doing is we're depositing the extra charges on the surface of that pipe. Remember, on a surface, the extra charge is going to get deposited along the top. It's going to be equally opposite. So it's not that you're like making a current or magnetic field or you're doing anything like that. All you're doing is you're taking charges and you're putting them along the edge of the material. What? Something that you're really familiar with?
Or you can leave. If you're gonna be doing that, you can leave.
Or go do airsoft.
Are there gonna be any questions where
What's up?
Are there gonna be any questions where it asks like which one represents the correct like electric field with the test charge going through?
I don't know exactly how to test works. I'm sorry. What about drift speed? I don't care about drift speed with this one. Okay, now we got there. Gentlemen, together. And we started to find this thing called a capacitor, which was just 2 plates of metal with some space between them. If they touch, they can't start a charge because current can flow. They're isolated by this thing called a dielectric. Okay, and the capacitor wasn't particularly hard. It really wasn't. But at the time, it started to scare us because we had been away from math for a little bit of time, and it came back. And capacitors depend on all kinds of crazy shit in reality, but in reality, we make them pretty simple for this class. The first is the capacitance of any capacitor is equal to the charge on its plates divided by C equals Q over V, the voltage of the source charging them. So let's just do like 2 quick examples of these. Let's say you have a, I don't know, let's do 600 microfarad capacitor. What's the voltage going to be?
There's gonna be a lot of questions on like the micro.
What's up?
What is Q?
What? Charge.
There's gonna be a lot of questions on like the micro.
On this? This would be like a brief workout question. You need to know what micro is.
Yeah, but are you like simple?
They'll be within the problem. They won't be supposed to be a problem. They'll always be within a workout problem.
The C equal capacitor.
Okay, what voltage we gonna use?
69.
69 power. Apply. What charge? Okay, so again, excusing my bad handwriting. C equals Q over V, so what's the charge of plates? It should be like a 30-second algebra problem if you remember C equals Q over V. Farads. The basic unit is Farads.
Yeah. That order's
Q is what you're solving for.
What's
Charge. Capacitance.
Pass it off.
Alright, here we go.
I'm about to ready.
No, he just met me outside.
No.
A guy named Brock.
What? This F is the unit, C is the variable. So, gentlemen, tricky bit of this. The units of C are F.
No.
Farad. Units of Q are Coulomb.
That's
Right. It's one of my favorite questions from one of your tests this year. What's if I has units of C, Q, or F, and like 80%
I got that
of you,
shit.
yeah, 80% of you just bit the bait. It's great. Yeah, that's so, I very much enjoyed that question. All right, we good with this one?
Some men just like to watch the world burn. Tim Nendick.
So 600 times 10 to the negative what? 6. Good. Equals my variable over 69. So I get 69 times 600 times 10 to the negative 6. That's basically equal to 70 times 600. So that's 4,200. So I'm going to get what? 4.2 give or take times 10 to the negative 5th. Is that what you got?
Yeah.
Yes, no?
Oh shit.
69 times 600 times 10 to the power of negative 6 equals 0.00414. I was off by power of 4.
Come on.
Whatever. I don't give a shit, really.
Wow.
Dude, he's so smart.
He's so smart.
Can we round that 4 up?
I would take.
You're coming
You're
for
right. You're looking for 420.
What?
Yeah. It would be if you use 70 and 69.
What?
It's like a $3 delivery.
Right? I missed that.
I mean, in a point like this, it's really
Yeah, I'm just going to salt my mouth like
Okay.
Lincoln Lawrence.
I'm gonna try it. Or yours. What is your
REQ. Equivalent resistance. We get there about 15 minutes at most. Okay. All right. On its own, I think this equation's easy. The only trick is knowing what the variables stand for. And my kids, at least, you're given this equation on your sheet. Wilson's, I'm assuming you're given it too. You might email him and ask him for a copy of your equation sheet. So make sure you write down this, and if you're writing down, write F and C down as your units. Okay.
Ciao, Tim.
Are we given every equation?
Yeah, you're given every equation you need. There are a few extra problems in there, but whatever. Okay. The other equation for a boy, did I ask you a question about plate spacing? Really? Hold on, did I really do that to you? That would have been a dick move.
Come on, don't do it.
Wait, plate spacing like the doping thing?
No.
Is that like the tectonic plates?
Nah. Good. I fixed it. Okay. We're comfortable. This is all I mean by capacitor equations. I just need questions that like this level of
Are
difficulty.
there gonna be any different types of questions like that? Like we have to like.
No, it's really, I mean, you can solve for C, Q, or V, whatever you're doing. I mean, you've got 3 variables. It's an inverse proportion, so it goes right. All right, let's get to the big boy. The big boy in electrostatics was called Coulomb's law. Coulomb's law is not hard. Mr. Wilson's kids, I don't know quite how he's going to deal. I know you're going to see at least one question about this. I know for certain you're going to see at least one question. Yep, F equals some number K, the magnitudes of Q1, Q2, and the raise of it. And the observant around you would say, oh, that's basically gravity, and you're right. Except instead of a tiny number, we have a big number.
Is it K a constant?
It is a constant. And you're always going to be going here. And this is it. 8.99 times 10 to the 9. It's a huge number. Basically, we're going to take these things and we're going to make them quite a bit bigger. So I don't particularly care how we do it. We can find the force between them. We can find the charge on an object. Which one do you want to do?
Charge of an object.
Charge an object. Okay.
Yeah, which is harder?
Well, I mean, I think all of you are capable of just plugging things into this equation.
What's going to be asked on the final?
So,
let's do charge.
Let's say you
What's
got.
the exact question on the funnel?
Pretty much all. Let's say you got these. Well, I'm not going to do that. These two blue balls.
Yeah, Tim!
Okay.
Oh my God, you
Let's say they're identical in every way.
Oh
Oh yeah. Yeah. Okay, let's go. No. Because it's still a class. Let's go. Now we've got these two blue balls. They're identical. They're identical in every way, shape, and form. They're separated by some distance. How far apart are we going to make them?
12 meters.
Let's go with 12 nanometers. Let's make them very small. So they're very close together. And let's give these each some charge Q. And Q is what I'm looking for. And let's say they're repelled by some force of, I don't know, let's say they're being repelled by 1,000 newtons.
420. Bitch.
1,200 newtons. You just made your math harder. Way to go.
Damn right, Tim.
4,200 newtons. Let's say they're pushing a bar with 4,200 newtons. I have all the information I need to solve for the charge. So this could look like find the charge on an object. They will always be identical, otherwise I have to give you way more information. Right? So I'd have to give you way more information than this.
Yeah, you guys give us Q1 and Q2. Wait, no.
Right.
Aren't those like constants? They're like
But I'm
1.6?
telling you that these two charges are equal, so it's fine. Because what I get is a 4,200 equals my 9 times 10 to the 9th. I'm just going to round that up. It's close enough.
And that's a constant, right?
We're gonna be
Yeah.
given K, right?
Yeah. A Q1 and Q2. It's just going to be Q squared, right? Because it's Q times Q is Q squared over 12 nanometers squared. Okay, 12 nano. What's that? Good.
Nice.
Squared. And well, lots of times students will get tempted to just cancel these squares because you're still learning algebra. Don't do that. Okay.
Got it, Worry?
From here, it's pretty easy to solve. I'm not going to let's go ahead and actually show all the steps. 4,200 divided by 9 times 10 to the 9. All of that number times 12 times 10 to the negative 9th squared. And that whole number needs to be square rooted. Okay, I know my work is a bit big, but just solve for Q. What's up?
On the equation sheet, does it tell us that K is...
Yes, you're giving K for me.
Where's the shit looking?
So Q squared.
Oh, okay.
So let me...
Is it Q 1.6 times like...
It is for an electron or a proton to negative 19. But it's not always in this case. So, you get here and you can do it however you want. Just do the algebra. Because for the sake of time, I'm just going to write them out quickly. Again, if you need help doing the algebra, that's a different story. But my guess is most of you at this point in your lives are pretty good at algebra.
Or he's still shitty at algebra.
That's true.
He goes, that's true.
That's true.
And I get an answer of 0.008. I don't know if anyone else has gotten there, but I get 0.008 coulomb, which is actually a ton of charge, given the fact that they're basically in atoms with a part. For this to happen in real life would be pretty close to difficult. At that point, you're probably making lightning.
Q is Q.
No, my guess is this is happening inside of lightning or a superconductor. But it's not crazy. It could happen. I mean, consider what 4,200 newtons is. If you have 4,200 newtons of force, that's like having half the people in this room standing up on top of my hands. Right? It's not quite... It's like having those 4 people standing on top of my hands. Not quite half.
No, your chance is huge.
It's like having this side of the room minus come on, not my hands.
It's like just having chance on you.
Yeah.
Actually, just like having my cock on your
No, so this is, so that's true. No, so let's go.
Then you use that comeback like
I know.
You used that fucker on the last day.
Yeah, but it's the end of the year. How come back straight left?
It's too easy for it to happen.
Chance is like, damn it, you got me.
Okay. Now, my guys. Wilson's guys, I don't think he's going to have you do this. My guys, you certainly will. Pay attention really fast. Okay. My guys, when I ask